In this lecture, I'll cover solving differential equations by the Laplace transform method. Now, we talked in an earlier lecture about how the differential equations that can be solved by Laplace transforms must be linear, time invariant, and ordinary. In this approach, there are three steps. The first is to take the Laplace transform of each term. The second is to solve for the dependent variable, for example, x of s or f of s. And generally you do that with algebra. And then the third step is to take the inverse Laplace transform of each term. Now, to get the equation into a form that you can take the inverse Laplace transform of each term, you may have to do a partial fractions expansion. The one nice thing about the Laplace transform method is that it's going to give you the complete solution, which means it's going to have both the particular solution and the homogeneous solution. It's going to do that in a single step. So when you do this method, you don't have to solve these two parts separately and then add them together in the end. The Laplace transform method will do both simultaneously. The other thing is with the Laplace transform method that you can include the initial conditions. So you can take into account, for example, in a mechanical system, you could take into account the initial position or initial velocity of your system. And in a thermal system, you could take into account the initial temperatures. So let's do a couple examples. Here we have a differential equation, x double dot plus 3x dot plus 2x equals 0. So you can see that this is a linear differential equation. It's homogeneous, time invariant, and it's ordinary. The initial conditions for this example are that x at time 0 equals 10 and x dot at time 0 equals 5. So to give you an example, this differential equation may model a mass spring damper system, which we'll see once we move into the mechanical section of this class. And in this case, then x would represent the position, x dot would represent velocity, and x double dot would be acceleration. So looking at our initial conditions, x of 0 equaling 10 would mean at time 0 our position in the x direction would be 10 units, and the initial velocity would be 5 units. So our first step is to take the Laplace transform of each term. So we have an x double dot, we have an x dot, and we have an x term. So we have to take the Laplace transform of each one of those. So let's start with x. So the Laplace transform of x is x of s. So we're converting from the time domain to the s domain. The Laplace transform of the x dot term, so that's the first derivative of x with respect to time, is s, x of s, minus the initial position, x at some time 0. And the Laplace transform of the second derivative of x with respect to time, or you can think about that as the acceleration, is s squared x of s minus s times the initial position minus x dot of 0. So now we have the Laplace transform of each one of the terms in our differential equation. So now we can substitute these in. So by making the substitution, now we have s squared x of s minus s x at time 0 minus x dot of 0 plus 3 times s x of s minus x of 0 plus 2x of s equals 0. So that's our differential equation where we took the Laplace transform of each of the terms in the time domain, and by using a Laplace transform table we've converted that into the s domain. So that's the first step of this solution method. Now the second step is to solve for x of s. So we can factor out our x of s, and that leaves s squared plus 3s plus 2. And then we can put our initial conditions on the other side of the equation. That'll be 10s plus 35. Okay, so you may remember up here that we had these terms that were our initial conditions. Here's s x of 0. Remember, x of 0 is 10, so this is really 10s. This is a minus x dot of 0, so that was 5. And now we have another 10 here, but we're multiplying it by 3. Okay, so together this becomes 10s plus 35. Okay, once we move it over to the right-hand side of the equation. On the left-hand side of the equation, this is all a negative. So if we continue the solution, now we have x of s equals 10s plus 35 divided by s squared plus 3s plus 2. Now, we're not going to find this form of this equation in the Laplace transform table directly, so what we need to do is do partial fractions expansion to get it into a form where we can just do the inverse Laplace transform by looking at the terms in the table. So first let's solve for a1. So to solve for a1, we're going to multiply each term by s plus 2. So that's the denominator in the a1 term. So what we get on the left-hand side of the equation is we get 10s plus 35 divided by s plus 1, and that will equal a1 plus a2 times s plus 2 divided by s plus 1. Okay, so the s plus 2 in the a1 term canceled, and the s plus 2 on the left-hand side of the equation, that also canceled. So the next step is to let s equal minus 2. Okay, now over here in the numerator we have a minus 20 plus 35 divided by a minus 1, and we have an a1 plus 0. So we see that a1 equals a minus 15. So let's follow that same procedure to solve for a2. So for a2, we're now going to multiply by s plus 1, which is the denominator in the a2 term. Okay, so on the left-hand side of the equation, we're going to be left with 10s plus 35 divided by s plus 2. So I said we're going to be multiplying by s plus 1. I hope that's what I said before. And in the a1 term now is s plus 1 divided by s plus 2. And then we have a2 because the s plus 1 cancels when we multiply it. Okay, now in this case we're going to let s equal minus 1. And let's see how this goes through. So this is a minus 10 plus 35 divided by 1. That equals 0 plus a2. So in this case, a2 is going to equal 25. Okay, so that's our two terms. Now we know what a1 and a2 are, and we can expand our fraction and take the inverse Laplace transform of it. Okay, so we move down here. Here's our x of s. It used to, in the other form, equal 10s plus 35 divided by the quantity of s plus 1 times s plus 2. But now we have these, we solve for a1 and a2, and so a1 is minus 15 divided by s plus 2, and we have a positive 25 divided by s plus 1. So these are terms that are in the Laplace transform table, so now we can just take the inverse Laplace transform. So this is our final step. Inverse Laplace transform of each term. Okay, so the inverse Laplace transform of x of s is going to equal x in the time domain. Inverse Laplace transform of minus 15 divided by s plus 2. That equals minus 15 e to the minus 2t. And the inverse Laplace transform of 25 divided by s plus 2. That is 25 times e to the minus, oops, I made a mistake here, didn't I? So this should really be minus 1, correct? So this should be a plus 1, or e to the minus 1t. So now we can substitute these terms back in, and we have x of t equal minus 15 e to the minus 2t plus 25 e to the minus t. And that's the solution to our differential equation.